All right, we're back. We're on page 2 of notes 12. We're talking about something called definite integrals. So far, instead of talking about those, we've talked about velocity, which is like your rate of change of position. And then we talked about displacement, which is just like what's at the end of your journey, what's your position relative to where you started? Are you to the right, to the left, above, below, and how far, right? And then we ran into this idea of negative or signed areas as we did this. And it's kind of a new idea, but nothing about it has ever bothered me. It's like sometimes you're going to the right, you have a positive velocity. Sometimes you're going to the left, you have a negative velocity. Like, yeah, why not? So what's negative area? It's not that bad, right? It just means that it's a region that falls below the axis, below the horizontal axis. So let's see if we can deal with one where our velocity changes, like sometimes positive, sometimes it's negative, which kind of makes sense because things move back and forth. So the graph below shows velocity moving in a straight line in feet per minute. Calculate both the object's displacement and its distance traveled. That's a slightly different idea. So let's see if we can do that. All right, let's find, but first let's do a lot of geometry and like carve this up, find some areas, see what we can do with that. So I think it makes sense to cut it here. I think it makes sense to cut it here. Probably makes sense to cut it here, and then we'll do a triangle there. So you just have to make your choices, and it doesn't really matter as long as you find the correct areas for each. So what I'm going to do here for this first part is I'm going to do this square, which is 2 by 2. So that's 4, but negative 4 because it's below the axis. It's really 2 by negative 2. And then this is 2 by 1, but half of it, so just 1. So this part here in total is negative 5. So it was negative 4 for this, and then negative 1 for this. Okay, I'm kind of reassuring myself when I do that. This is half of a 2 by 1, so 1, but negative. This will be 2 because, I mean, it's kind of easier to see. It's 2 by 2, and then half of that. Here we're going to do 2 by 1, and then half of 2 by 1 is 1, so overall 3. This is definitely just 0.5. And then here we're going to do half of a 2 by 3. So 2 by 3 is 6. Half of that is negative 3. Well, half of that would be 3, but negative because we're below. So we got all our things. So displacement. So displacement, think about what's happening here. So if you're displacement, first, you're at your starting point and you go 6 units to the left, right? So now you're 6 units to the left of where you started. Now, wherever you are from there, you're going to go 5.5 units to the right. So if you started someplace and you went 6 units this way, and then 5.5 this way, you're actually only 0.5 units from where you started, and you're to the left of it. Then from there, so you went 6 this way, 5.5 this way, then you're going to go 3 this way again. So overall, that's what we're trying to do. We're trying to say, and actually, I don't know why I'm not like actually drawing that. So maybe, you know, you go 6 this way. Trying to get, there we go, 6 this way. Then you go 5.5 this way. And then from there, you're going to go 3 to the left again. So that one's going to be the hardest. There, I think. That's wrong. Well, if I'm using the scale, I'm trying to use the x-axis. I have to go 3. So I'm like kind of at 5.5. I got to end up at 2.5. So let's aim there. There. I think that our total displacement is going to be, I don't know, to the left. That was not easy. Hold on, let me do this. Here, let's say this is negative 6. And then this one was 5.5. And then this one is negative 3. So, you know, it's weird. So the reason that it's weird is that I started at 6 and I went back towards 0. And like really, so like 6 is where I started. I made it overly complicated, basically. All we need to do is add these up, though. So our displacement is going to be negative 6 and then plus 5.5 and then minus 3. So that's negative 9 plus 5 is negative 4, plus 0.5 is negative 3.5. So how does that work in the context of this? All right, so I said 6 was my starting point, which was like, that was bad. That was my downfall to begin with. So 6 was my starting point. I went 6 this way. I go back 5.5, and then I go 3 this way, and I end up at 2.5. 2.5 is 3.5 to the left of 6 where I start. My displacement is negative 3.5. What are we moving in? Feet. So negative 3.5 feet. I end up 3.5 feet to the left of where I started, regardless of where I started. For some dumb reason, I started at 6, and then it became more complicated. If I had started at 0, gone 6 to the left, that puts me at negative 6. Go 5.5 to the right, that puts me at negative 0.5. Go 3 to the left, that puts me at negative 3.5. I started at 0, I end at negative 3.5. I'm 3.5 to the left of where I started. Easy. For some reason, I started at 6. Poor choice. Now, distance traveled is kind of a different ballgame. So, I mean, look at this. I started here and I went 6, then I went 5.5, then I went 3. It's like the car's odometer, right, which counts how far you've gone, does not care what direction you're going in. It just counts how far you've gone. So our distance is actually related to displacement, kind of. What we're going to do is we're going to do the absolute value of negative 6 plus the absolute value of 5.5 plus the absolute value of negative 3. And that'll be 6 plus 3 is 9, plus 5.5 is 14. Point 0.5. Sometimes I confuse 5s and Fs, which maybe some of you do also. I don't know. Our distance traveled is way bigger than our displacement because we traveled 6 units and then 5.5 units and then 3 units, right? Yeah, they were in different directions, but it's still traveling. Distance traveled tends to be, it's either going to be greater than or equal to displacement. It's never going to be less. Displacements can be negative, they can be positive, whatever. Distance traveled, always positive, always got to throw these absolute values in here because it's non-directed, right? It's just a distance, not a directed distance. So this is 2 ideas. Let's kind of summarize some things, see what we know, see what we don't know, see what we got to learn. All right, so every calculation that we just did above to find the displacement of a particle had a special name. And the special name is a definite integral. We were just calculating definite integrals. One application of definite integrals is to find displacements from a velocity. There's a lot, there's like an infinite number of applications of definite integrals. They all basically add up the total accumulation of a change, right? Velocity is rate of change, add up rate of change, you get apparently displacement if it's velocity. The notation is kind of interesting, and maybe you've noticed it on your calculator. Maybe you played around with it when you were doing some other problems. I know in videos I've used it a little bit. So for the last, I guess for all of them, I didn't notice this. We were always going from 0 to 10. This is the correct notation for every problem that we just did. So I'm trying to find a different color. Every problem we just did was this. And the way you would say this is, you would say this is the integral from 0 to 10 of v of t dt. dt is basically telling you the variable is t, and v of t is the function that is involved that you're finding the area, the total accumulated signed areas of, and 0 is where you start and 10 is where you end. It's the definite integral, or just the integral from 0 to 10 v of t dt. I did not notice actually that all of them went from 0 to 10, so that was clever of me. 0 to 7, sorry, what am I even saying? The elongated S is called an integral sign, and it's literally an elongated S. It comes from summations, right? Summations are sigmas. Capital S became our integral sign. And you can read this way, which I've already said a bunch of times. The answer to a definite integral is a number. So can't stress that enough. The answer to a definite integral is a number. Definite integrals are numbers. They just look really funny. And then the meaning depends on the context of the problem. So in everything we did so far, the meaning of our definite integral is basically the displacement. So displacement is a very common interpretation of a definite integral, but there's a lot of them. And then dt, I think of as kind of as t changes or delta t, right? You're doing like base times height, and the base is delta t, and the height is like v of t, or the function. It basically tells you the variable that you're dealing with, and it tells you that in this notation that 0 and 10 are t values, right? If it said dx, they would be x values. So it just depends on what the variable is. Here are some properties. Go over these kind of quickly, and then we're just going to use a ton of them in the next couple of pages, so don't worry about that too much. But the definite integral from a to a of f of x dx is 0. How can you think about this? Well, if you don't go anywhere, you don't have any displacement, right? If no time passes, you don't go anywhere, so you have no displacement. So the definite integral from a to a, like if your velocity is whatever, and you want to know like what's your displacement on the time interval from t equals 5 to t equals 5. T equals 5 is one time. There's no displacement. So you're just going to get 0. The integral from a to b of f of x dx is the negative of the integral from b to a. So the key thing here is we have reversed. Here's a, and then here's b, here's b. We flipped the bounds. If you flip the bounds, you change the sign. The way that I think about this is kind of in terms of like moving left and right, or rewinding a video, right? So you play a video in forward, right? So you play a video, you go from A to B, like, I don't know, 0 minutes to 5 minutes. If you rewind a video from 5 to 0, you should just get the negative of what you got when you went from 0 to 5. Like, it makes sense. You're rewinding. You know, if you watch the characters move around and then you rewind from 5 back to 0, they're going to be where they started. They literally undid everything they did to get there. So you just get the negative of the integral from b to a. So if you flip the bounds, you change the sign. Another property. So if you go a to b and then b to c, so let me try to highlight that. You go a to b, and then a to b, b to c, a to b, b to c. That's just the same as going from a to c. So if you go from a to b, get an answer, then you go from b to c, get an answer. You might as well have just gone from a to c and added those. And so when you add them, or basically you can add them, they're just numbers, so you can add them. The next two are weird-ish. I mean, they're really not when you think about it graphically, but if you have an even function, so it's required that this be even. It's a big deal. If you have an even function, then you can actually say that the integral from negative a to a is just 2 times the integral from 0 to a by symmetry. Draw a symmetric function. So draw like y equals x squared, for example. So let's see, y equals x squared. Oh my gosh. That, why are you auto-shaping me there? Okay, there, right? That's y equals x squared, sort of. Let's say this is like -3 and this is 3. Well, this region definitely has the same area as this region. So why not just go from 0 to 3 and double it? That's basically the idea. Anytime you can use 0 as a lower bound, I recommend it. It doesn't really mean much now, but I definitely recommend it. Then if we have an odd function, so this is only applicable to odd functions, but it's pretty cool. Well, it's only definitely applicable to odd functions. I guess you can make up a non-odd function for which this would be true. But the integral from negative a to a is just going to be 0. So why is that? Well, think about, I think that y equals x is maybe the easiest odd function to deal with. So let's look at y equals x. So the idea here, so that's like, it like auto whatever is there. So I know that's like the right angle, but okay. So if this is a, then this would be negative a. But because of signed areas, let's say that this has an area of k. Well, this, by symmetry, has got to have an area of negative k. And since you can add them up when you go from negative a to a, this negative a doesn't look that great. When you go from negative a to a, you're just going to do negative k plus k, you're going to get 0. That's going to happen every time your function is odd. I highly encourage you to look for that, because when that happens, you save yourself a ton of time. So even functions, save some time. Odd functions, save some time. Got some properties. Probably the weirdest one, I think, is maybe this one, but not if you think of it in terms of rewinding a video, right? Like if you're going from A to B, it moves you like 8 units to the right, then going from B to A should give you negative 8 feet, right? 8 feet to the left to take you back to where you started. So anyway, we'll be back in the next one. We're gonna do like a ton of these. And so we'll see how that goes. So I will see you in the next video.